In this video, I'm going to discuss prime factorizations, and first we should start by talking about what's a prime number. Well, a prime number is a natural number. It's greater than 1, and it only has factors 1 times itself. So if you're trying to build it by multiplying, the only way you can is multiplying 1 to the natural number. For instance, here's our first primes, and 2 is prime because the only way to make it through multiplication is 2 times 1. The same for 3 or 5 or 7. Contrast that with a composite number, which again is a natural number, and it's also greater than 1. But it's all of the natural numbers greater than 1 which aren't prime. Here's the first few composite numbers. 4 is composite, for instance, because besides 1 times 4, you can also make it with 2 times 2. Now, to prime factor a number, what we do is we continue to break the number down into factors until all the factors are prime. For the number 12, the prime factorization would be 2 times 2 times 3. They're all prime numbers. On the other hand, 2 times 6 is not a prime factorization of 12. It is a factorization. It just doesn't happen to be the prime factorization, because 6 is composite and can be broken down into 2 and 3. Here's some factor rules which will help you break numbers down into factors. Sometimes these are called divisibility rules. The rules here are for 2, 3, and 5. 2 is a factor if the last digit of a number is 0, 2, 4, 6, or 8. That is, if the number is even. 3 is a factor if when you add the digits, you get a number which itself is a factor of 3. And 5 is a factor if the number ends in 5 or 0. There's like rules for 10 and some other things, but for instance, if 10's a factor, then so is 2 and 5. So I usually just use these 3 to start with. I'd like you to decide if the numbers I show you next have 2, 3, or 5 as a factor. For instance, 42 would have a factor of 2 because it's even. It ends in a 2. It would have a factor of 3 because 4 plus 2 is 6, and 6 has a factor of 3. It wouldn't have a factor of 5 because it doesn't end in 5 or 0. What do you think of this number? Well, 310 does have a factor of 2. It ends in a 0. It does not have a factor of 3 because 3 plus 1 plus 0 is 4. And 4 doesn't have a factor of 3. It does have a factor of 5 because it ends in a 0. How about this number? We don't have a factor of 2. The number isn't even. We do have a factor of 3 because if you add the digits, you get 24, and 24 has a factor of 3. Notice if you add the digits of 24, you get 6, and 6 has a factor of 3. My point is, if you add up the digits and you don't know if that number has a factor of 3, you can continue to add the digits to find out. And 5 isn't a factor since it doesn't end in 5 or 0. Here's the last one we'll look at. This has a factor of 2. It also has a factor of 3. It also has a factor of 5. Once you know the factor rules, you can find prime factorizations by building a factor tree. For instance, if I wanted to find the prime factorization of 20, I'd first have to recognize that it's composite. I might think of the factors of 20 as being 5 and 4. 5 being prime, I circle. I don't need to worry about that factor anymore. But 4 is still composite, so I'll need to break that down into 2 and 2, both of which are prime. And so I'm done. The prime factorization of 20 would be 2 times 2 times 5. Oh, but you say, I didn't want to use 5 and 4. I wanted to use 2 and 10. That's fine too. Notice that if you start with 2 and 10, you again end up with 2, 2, and 5 as factors. And so the prime factorization in either case is going to be 2 times 2 times 5. This idea is so important, it's known as the fundamental theorem of arithmetic. That is, every natural number greater than 1 has a unique prime factorization. Here's a procedure for finding prime factorizations. Start by trying to find the factors when you have a 2 or 3 or 5 in the number. Next, if you have some factors left, you have to start dividing by all the primes up to the square root of the number. For instance, you need to try 7 and then 11 and then 13. Make sure you have a calculator to do this. And then when you're done, you kind of want to write all the factors smallest to largest just to be nice to other people looking at it. So if I was going to find the prime factorization of 24, for instance, I'd say, well, 24 is 2 and 12, 2 is prime. 12 is 2 and 6, 2 is prime. 6 is 2 and 3, both are prime. So the prime factorization of 24 is 2 times 2 times 2 times 3. Try this one. When I look at 315, I notice it ends in a 5, so I usually start with 5 and 63. 5 is prime. 63 I found using a calculator. It's not something I knew off the top of my head. So I just divided 315 by 5, and I found what other factor makes up the 315. 63 has a factor of 3 since 6 plus 3 is 9. So I know that 63 is 3 times 21. 3 is prime. 21 I think of as 3 and 7. Both are prime. The prime factorization is 2 3s, a 5, and a 7. Try 119. 119 doesn't have a 2, 3, or 5 as factor, so I need to go to the next one, 7. And when I divide 119 by 7, I find the other factor is 17. Both are prime, so the prime factorization of 119 is 7 times 17. How about 495? I would notice first that 5 is a factor, and I'm left with 99. When I look at 99, I think of 9 and 11. 11 is prime, 9 is composite. The factors are a couple of 3s. And so 495 has 2 3s, a 5, and 11 as factors. Next, we'll move on to using prime factorization to reduce fractions.